Hello guys, it's me again, Engineer Makalinaw. Let us discuss about Euler's critical buckling stress of built-up symmetrical sections. Let us have a problem. The built-up section as shown is used as a column in which the ends are pin-connected both at top and bottom, about x and y axis, and laterally supported 3 meter from the bottom about the x-axis. Height of column is 7 meter. Calculate the Euler's critical buckling stress. Use recommended K values. If you're going to look, you can see here the built-up section. This is made of channel and 2 angle bars. You see the properties of a section. Before we start solving that, let us discuss what is Euler's critical buckling load. Basically, when you say Euler's critical buckling load, that is the greatest load that can be applied before buckling of column. So it is given by the formula P critical is equal to pi squared EI over KLU square. What is buckling, by the way? So if you're going to apply a load that is greater than its critical buckling load capacity, it will buckle like this. There will be a lateral deflection and it will cause instability. Therefore, your column will somehow collapse. What is Euler's critical buckling stress? It is the actual stress that corresponds to critical buckling loads. If you're going to divide the critical buckling load to the area, so I just use FCR for the critical buckling stress, and you're going to manipulate it algebraically, you will find an equation like this. Pi squared E all over KL over R square. KL over R is the critical slenderness ratio in a certain column or compression member. Take note of this. If you're going to get the critical slenderness ratio, you have to get the greatest value, because the greater the value of slenderness ratio, the more it is weaker. So it means that the crucial part of this discussion is about determining the critical slenderness ratio. So what are the rules? Number 1 is determine the radius of gyration about the principal axis. Number 2, determine the effective length based on end support condition and lateral supports, if any, on each plane of analysis. And number 3, determine the largest value of slenderness ratios. Of course, the critical slenderness ratio for a certain compression member is the largest slenderness ratio occurring in a certain column. So let us discuss it one by one. So basically, the hardest part of the solution is number 1, because it involves calculation of properties of sections. R is the square root of I over A. I is the centroidal moment of inertia. Let us discuss it one by one. Rules in determining the critical slenderness ratio. Principal axis is a set of axes perpendicular to each other that passes through the centroid, which contains the maximum and minimum values of moment of inertia. For example, this oval is not only an oval, it illustrates any section. This is the principal axis. These axes are passing through the centroid and they contain the maximum and minimum values of moment of inertia. This axis, which contains the maximum moment of inertia, is often called the major principal axis, and the axis that contains the minimum moment of inertia is what we call the minor principal axis. So it means, sir, before we get the radius of gyration, we should determine first where is the principal axis. Of course, in case of symmetrical section, the principal axis are the axis of symmetry and the axis perpendicular to it. So you're very lucky because you're not going to locate where is the principal axis if your section is just a symmetric section. Say, for example, you have a channel bar. This line is the axis of symmetry. The centroid will pass on the axis of symmetry. You form two perpendicular axes. These are now the major and minor principal axis. The axis of symmetry is not always the major principal axis. This is just only for my illustration. It might be axis of symmetry is the minor principal and this the other one is the major principal axis. This statement logically holds true. For example, you have an I section wherein both of the axes are axis of symmetries. What about, sir, if a certain section is not symmetric? By the way, guys, why is the axis of symmetry our principal axis? I will explain it later on the unsymmetrical section on my next video. But let us just talk a little bit about it. So, if a certain section is not symmetric, say for example, an angle bar, you really have to use the product of inertia to be able to determine its principal axis. let us go back to the problem and let us solve the centroidal moment of inertia of built-up section about the y-axis. It says that inertia at any axis is equivalent to the summation of centroidal moment of inertia of each section that comprise our built-up section. This is the transfer term, which is the summation of AD square. This is the figure before. You're not going to solve for the location of the centroidal y-axis because it is symmetric about y. So therefore, this line of symmetry is automatically your neutral axis parallel to the y direction. Going back to the formula, we all know that if you're using this, the moment of inertia of each section that you're going to sum up in this term should be the axis parallel to the axis of consideration. So let us get back to the properties of section. So the first thing that you should keep in mind is you must know how to interpret the properties of section. You can see this section properties in Asep Steele handbook. You have here the area, means that's the area of the angle bar, and Ix is the moment of inertia about this x-axis. Basically, the intersection of x and y-axis is the centroid of the section. Ix is 10.09, so this is the moment of inertia about x, and Iy is 3.56 times 10 to the 6 millimeter to the fourth. So this is the moment of inertia about the y-axis of that single angle bar. And for the channel, so this is the moment of inertia about x, and this one is the moment of inertia about y. If you're going to sum up all the centroidal moment of inertia that is parallel to the centroidal y-axis, keep in mind how the section assembled in the built-up sections. Each figure is rotated 90 degrees. If you rotate it 90 degrees, the axis that will become parallel to the centroidal moment of inertia about y will be the centroidal moment of inertia about x of the angle sections. This is the angle bar rotated 90 degrees. It is very, very obvious that this axis will be the one parallel to this centroidal y-axis. And for channel bar, you're also going to consider this value of moment of inertia because you rotate it 90 degrees. Therefore, this axis will be the one that will become parallel to the centroidal y-axis. This 2 is the Ix of both channel bar. Since you rotated it, it became parallel now to the y direction. And for channel bar, you're going to sum all of it. That's 88.74 times 10 to the 6th power millimeter to the fourth. These are the centroids of the sections. In this formula, summation of centroidal moment of inertia of each section parallel to the y-axis. For summation of AD squared, we have to get the distance of each steel section through the centroidal y-axis. You can do it by going back to our steel section property. Take note of this, guys. Since you rotate the angle bar 90 degrees, this distance now will be the distance y, which is 52.39. So the centroid of the other one, it is just symmetric on the right side. So this one is 52.39 also. See, the centroid of the channel bar coincides with the centroid of the whole built-up section. So therefore, the distance for channel bar is 0. Summation of AD squared. The area for channel bar is 7,200. The centroid of the channel coincides with the centroid of the y-section. That's why it is 0 square. Plus, for the angle bar, this is the area of a single angle bar, and this is the perpendicular distance of the centroid of the angle bar from the centroidal y-axis. So you have 52.39 squared plus another angle. So basically, you can just multiply it by 2 if you want. The answer is 25.251 times 10 to the 6th power millimeter to the fourth. Summing up the centroidal moment of inertia parallel to the y-axis of each steel section, that is 88.74 times 10 to the 6th plus the summation of AD squared, which is 25.251 times 10 to the 6th millimeter to the fourth. It will give you a value equivalent to 113.991 times 10 to the 6th millimeter to the fourth. Solving for the radius of gyration about the centroidal y-axis, we should get first the total area of the whole section. 2 times 4,600, this is for angle, plus 7,200, this is for the channel bar. So the answer is 16,400. Square root of I over A, you have the radius of gyration about Y is equal to 83.37 millimeter. Let us now solve the radius of gyration about the centroidal x-axis. We're going to determine the moment of inertia about the centroidal x-axis. Following again the transfer formula, take note that this should be the moment of inertia parallel to the axis of consideration plus the summation of AD squared, which is, in this one, D is the distance of each steel section to the centroidal axis we are referring into. In this case, the centroidal x-axis. Since you rotated it 90 degrees, the x and y axis will switch their position. Therefore, for angle bar, the axis that will become parallel to the centroidal x-axis will be this 3.56 times 10 to the 6. Since there are two at the top, you have IY for this angle and you have IY for this angle. For channel bar, the axis that will become parallel to this centroidal x will be the original y-axis of the single channel. So this will be 0.915 times 10 to the 6th power millimeter to the 4th. Summing all of those values, we have 803, 5,000 millimeter to the 4th. We're going to locate the neutral axis because we need this to get the distance of each steel section from the centroidal x-axis. Since we don't have axis of symmetry parallel to the x direction, we have to use the Variance Theorem. You have to get all of the distances of each centroid of the steel section to the reference line. As you can see, since you rotate the angle bar 90 degrees, the x and y distance here of the centroid will switch their position. Definitely, this vertical distance is now the value of x, which is equivalent to 27.39. And more so, for channel bar, the vertical distance from the web of the channel will be 14.17, which is technically the x values in the steel section properties. If you're going to determine the distances of each centroid from your assumed initial reference line for the channel section, that will be 35.83 because the width of the flange is 50. So therefore, 50 minus 14.70, we have 35.83 millimeter. For angle, since this is 50 mm, the width of the flange, you just add 27.39, giving us 77.39 millimeter. For the Variance Theorem, total area y bar is equal to summation ay. You have to get the total area, 2 times the area of the angle section plus the area of the channel bar. You have 16,400. 7,200 times 35.83 plus 4,600 times 77.39. I just multiply it by 2 because they are just located on the same distance from the bottom. Solving this, you have 59.144 mm. So it means the location of centroidal x-axis is 59.144 from the bottom. To get the distance of each for angle, this is 77.39 and this is 59.144. Therefore, the distance for two angle is 18.246. And for channel, this 23.314 came from 59.144 minus 35.83. To get now the centroidal moment of inertia about x, you sum the centroidal moment of inertia we calculated before plus the summation of AD squared. For this term is for channel bar. The area of the channel bar is 7,200 times d squared, which is 23.314 square, plus 2 times 4,600. I just multiply it by 2 because the angle bars are located in the same d distance from the centroidal x-axis. Therefore, the answer is 15.01 times 10 to the 6th power millimeter to the 4th. The square root of ix over a, that is equal to 30.26 millimeters. We already get the radius of gyration about the centroidal x and the centroidal y of this symmetrical built-up section. If you are solving a built-up section, the hardest part of the solution is basically getting the centroidal moment of inertia because it involves getting all of those numerical solutions that I've shown you before. So that's very tedious. Let me show you the technique to get the centroidal moment of inertia about x and y of the whole built-up section and eventually getting the radius of gyration about x and y. That the moment of inertia about any axis is always equal to the summation of centroidal moment of inertia of each section plus the summation of AD square. We're going to get the centroidal moment of inertia about x and the centroidal moment of inertia about y. So the first thing that you're going to do is sum up all the moment of inertia of each still section parallel to the centroidal x-axis, which is the horizontal. So this one is 0.915 and this is 3.56. If you add that value, you're going to store it to A. And for the centroidal moment of inertia about y, you're going to add all of the centroidal moment of inertia of each still section parallel to the y-axis, and those values should be stored to B. For centroidal moment of inertia about x, you're going to add n sigma y square. So we're going to use this formula because areas involved here are all positive, no negative. So take note of this. If centroidal moment of inertia you are calculating is x, the standard deviation should be on y, because if you're getting the centroidal moment of inertia about the horizontal direction, all of the distance are measured vertically. And for I sub y, it should be plus n sigma x square about x-axis. And this one is for about y-axis. For about x-axis, you can just multiply the 3.56 times 10 to the 6 into 2. That is 2 times 3.56 times 10 to the 6th power plus 0.915 times 10 to the 6th power. And then this value will be stored to A. And for the centroidal moment of inertia about y-axis, 2 times 10.09 times 10 to the 6. Don't forget, we rotate it 90 degrees. That's why the Ix and Iy will switch their position. Plus 68.56 times 10 to the 6th power millimeter to the 4th. Then I'm going to store it to B. So let me show you on your 991ES calculator. If you are doing this, you go to mode 1, which is computation, for easier typing of the syntax. So that would be 2 times 3.56 times 10 to the 6 plus 0.915 times 10 to the 6. And then after type, you store it to A. Shift store A. And then press AC. You type this one. That is 2 times 10.09 times 10 to the 6th power plus 68.56 times 10 to the 6th power. And then you press Shift store B. Before you go to start mode, let us recall the section properties. At first, we don't know where is the location of the centroid of this figure. If you are getting the centroidal moment of inertia about x and y of the whole built-up section, you should have an initial origin first. You have to establish your initial reference line parallel to x and y direction. So what is my tip? If your section has an axis of symmetry, you can use it as your initial reference line. Case for example, this is symmetric on the y-axis. So therefore, this axis of symmetry parallel to the y-axis, you can use it as your initial reference line. And for x, since we don't have an axis of symmetry which is parallel to the x direction, you can just select or designate any reference line you want. So for convenience, we use the bottom line. Now, the intersection of those reference axes you designate is your initial origin. And from that initial origin, you're going to get the coordinates of the centroids of each section. So let's start with this one. With respect to the y-axis, the channel bar is coinciding with it because the centroid of the channel is on middle. So for the angle, the distance from the y-axis is 52.39, which is basically the value of y because x and y switch their position. For the vertical position, this is 35.82. This x is 14.17. So the length of the flange is 50. The width of the flange is 50. So 50 minus 14.17, that's 35.83. And for this one, since the x and y values which their position, the distance from here up to here is the x, which is 27.39. So you just add it into the width of the flange, which is 50. Therefore, it will give us a value equal to 77.39. Let us draw it here. The coordinate of this point with respect to our initial origin, or the centroid of the channel, will become equal to 0, and this one is 35.83. And for the coordinate of this angle bar, that is positive 52.39. For the y, that is 77.39. So for this one, this is obviously equal to negative 52.39. And this is 77.39 millimeter. You go over with your calculator and go to mode 3, 2, and then you turn on the frequency. So you press shift, set up, and then arrow down, 4. Turn it on. To avoid confusion, let me say that this channel is area 1 and the angle on the upper left is the area 2 and this angle on the right is the area number 3. You have x, you have y, and you have the frequency. I will also put 1, 2, 3 here. You will put the coordinates of each. Say for example, for area 1, which is the channel, you're going to put the coordinates. So for x, that is 0, and for y, that is 35.83. For the frequency, you're going to input the area, which is 7,200 square millimeter. For the angle 2, the coordinate for x is negative 52.39, and for y is 77.39, and the area of that angle is 4,600. For angle 3, that is 52.39, and this is 77.39, and this is equal to 4,600. So what is the advantage of this? You don't have to get the distance one by one, and you don't need to use the Variance Theorem to calculate for the location of neutral axis. Let me put it in the calculator. And then after inputting it, press AC, and then follow this formula. For I about x, you just press this, a plus n sigma y squared. So that would be alpha a plus shift stat for n and shift stat for 6. Let us divide it by 1 million to show it in terms of times 10 to the 6. And the value is equal to 15.01. The moment of inertia about x is simply equal to 15.01 times 10 to the 6th power millimeter to the 4th. Since you need the value of the radius of gyration about x, let me put it this way. If you want to get the radius of gyration about x, you simply take the square root of centroidal moment of inertia about x divided by the total area. You can actually press it continuously. You can just go directly to the Rx. You take the square root of Ix, which is this term, alpha A plus shift stat for 1, shift stat for 6 square. You divide the total area. Basically, the total area of this is the sum of the frequency, which is taken as the value of n. So you just divide it by n. So you shift stat 4 and then the one, put a parenthesis here for correct syntax, then press equals. The answer is 30.25. So the radius about x is 30.254 millimeter. We can now proceed directly to the value of ry here. That is square root of centroidal moment of inertia about y over a, which is the value of n, or the total value of the frequency. Press this one, the arrow, and then you edit this syntax. So for this, you replace it by b. This is alpha b. This n sigma y squared, you edit it. So shift stat for 3 divided by n, and then let's press equals. The answer is 83.37. So that is now the value of the radius of gyration about y. Okay, so you can practice it by solving other built-up section. And now let us move on to the next rules in determining the critical slenderness ratio. So the next rule is determine the effective length based on end support condition and lateral supports, if any, on each plane of analysis. We have a term called effective length factor. So that is the value that you should multiply on the unsupported length to convert the unsupported length into effective length. So basically, you have two values. You have the theoretical K value and you have recommended design value. We have a recommended design value because in reality, we cannot create a perfect or ideal support conditions. Say, for example, in real life, we cannot create a perfectly fixed support. That's why the value of K is adjusted to 0.65. That's just for example. Next, a very important thing about this is what we call the plane of analysis. What is plane of analysis? Plane of analysis is a plane perpendicular to principal axis, the plane in which buckling may happen. So it means if a certain column will buckle, you can see it in one of those planes. Let me show you a three-dimensional figure. This one is the centroidal y-axis of the built-up section, and this one is the x-axis. You can actually view it in two ways. You can view it in this direction, and you can also view it in this direction. Let me show you the figure if you're going to view it first in this direction. If you're looking at this plane, you can see this figure. This is the thin flanges of the channel. I'm going to show you also the plane if you're going to look on this direction. Our drawings are not drawn to scale. So please forgive me on my not so good drawing about this. The axis in which the buckling is happening about in a particular plane of analysis is always perpendicular. What does it mean? Say, for example, if you are looking on this direction, you will see this one. And if you're going to imagine it, the axis perpendicular to this plane of analysis, which is, you can view it in this direction, is basically our y-axis. In this plane of analysis, the buckling may happen about the y-axis. Let me call it buckling about y-axis. If you're going to use a property of section and you're analyzing this plane, you're going to use the property of the centroidal y-axis. If you're going to look on this direction, in which you can see it like this one, the axis perpendicular to this plane is the x-axis. So, therefore, buckling is happening here about x-axis. Basically, I'm not certain on which axis the buckling may happen. Meaning, we are not sure if the buckling will happen on y-axis or it will happen on x-axis. To be able to know where the buckling may happen, we are going to get which of them will have the greatest slenderness ratio. So let us go back to the statement of the problem before. The built-up section as shown is used as a column in which the ends are pin connected, both at the top and bottom, on both x and y axis, and laterally supported 3 meter from the bottom about the x-axis. Height of column 7 meter. Calculate the Euler's critical buckling stress. Use recommended K values. This is pin connected both at the top and bottom about x and y axis. It means about y axis and about x axis, both of them are pin connected like this. And it is laterally supported 3 meter from the bottom about the x-axis. This statement is very important because you should specify in which axis you're going to put the lateral support. The lateral support is being applied about the x-axis. So therefore, you're going to look on this plane. And then, you put the lateral support 3 meter from the bottom. So, it should reflect like this. So, what is the nature of the lateral support? Guys, the lateral support may be assumed as pin connected. So, calculate the effective length of a certain compression member. Effective length, L sub E, is equal to effective length factor K based on end support times the unsupported length. What is unsupported length? Unsupported length is the length of the member from support to support, meaning to say, the height of the column is 7 meters. If this is 7 meters, there are no lateral support in this direction. Your unsupported length here is 7 meters. And since, guys, the support from end to end is pin connected, whether it is recommended or theoretical, the value of K here is equal to 1.0. That's why the effective length here is equal to KL. Your K is 1.0 and your length is 7,000 mm. So let us use millimeter for unit consistency. 7,000 mm. We're going to divide it on the radius of gyration. Since on this plane, the buckling is happening about the y-axis, therefore, we should use R sub y. That's why it's very important to specify what axis is resisting the buckling on a certain plane. It's very important to know that on this plane, the buckling is happening about the y-axis so that you know the proper section property that you're going to use in getting the slenderness ratio. So in this case, that is KL over R sub y. So KL over RY. So that is equal to 1.0 times the unsupported length of 7,000 millimeter. And the value for RY, we calculate it before, which is equal to 83.37, and this is equal to 83.96. So guys, the slenderness ratio here has no unit because this is both same unit, millimeter, and this one is millimeter. Let us now move on to the other plane of analysis, which is the buckling about the x-axis. Let me give this point. So this is laterally supported 3 meters from the bottom. Therefore, this part is 4 meters. So definitely, if you are referring to this plane, you're going to use the radius of gyration about x, which is 30.26 millimeters. If you're going to consider this, you can see that there are two unsupported lengths, the 4 meter part and the 3 meter part. So therefore, in this plane, you have two values of slenderness ratio. So if you're going to consider this segment, this is pin connected and this is pin connected. Therefore, the effective length factor is also 1. If we're going to get the slenderness ratio here, that is equal now to 1.0 times the length is 4,000 millimeter all over Rx, which is equal to 30.26. This is equal to 132.19. And then we have another slenderness ratio here. 1.0 multiplied by 3,000 millimeter divided by the radius of gyration about x, which is equal to 30.26. So this is equal now to 99.14. And now, how to determine the critical slenderness ratio? The critical slenderness ratio is the greatest slenderness ratio we calculate on both of the plane of analysis, in which that is equal to 132.19. So, it only means that if buckling will happen on this compression member, the buckling will start to occur on this segment. This segment is the critical segment in terms of buckling because this segment has the greatest slenderness ratio. We are now ready to get the Euler's critical buckling stress, which is derived as follows. This is the winner, 132.8 slenderness ratio. To determine the Euler's critical buckling stress, that is equal to pi square E all over KL over R square. So that's equal to pi square times 200,000 for steel. E is 200,000. I hope that's clear. Over 132.19 square. Therefore, the critical buckling stress is equal to 112.96. The unit is megapascal. So this is the final answer. You can actually practice it by searching for other built-up section problems in which you are going to get the critical slenderness ratio. I hope, guys, you learned something in this video. The next lecture that I'm going to present here is what about if a certain section is an unsymmetrical section? Because in this video, I told you that the principal axis for symmetric section always passes through the axis of symmetry. So if a certain section is not symmetric, that's the time that you're going to utilize the concept of product of inertia. I'm going to show you the conventional solution and also the technique on your calculator, how to get it fast and efficient. So thank you guys. Please subscribe on my channel. Bye-bye.